So this lecture is all about nuclear chemistry, and we're going to begin by doing a quick review of the subatomic particles. The first person we're going to talk about is Thomson, who did the cathode ray tube experiment, and when he passed an electric field, he noticed that particles moved from the negative to the positive side, and so he decided to add one more part to this. Thomson decided to add positive and negative charges on the bottom and the top of the cathode ray tube, and when he added the electric field, he noticed that the particles moved from from the negative to the positive again, but this time it was being directed towards the top, which was a positive charge, and so he came up with the idea that the moving pieces or moving particles were negatively charged. Now, Rutherford came up with a gold foil experiment where he thought that if you shot alpha particles through this gold foil, and if J.J. Thomson's idea was true, then it would go straight through. But when he did the experiment, he noticed that they went in every which direction. So he realized that these were being deflected because there had to be some type of dense material in the middle of the atom that would deflect it, and the rest would be empty space. So Rutherford came up with that there was a very small dense nucleus with the that was positively charged and with electrons around the outside of the atom, which is mostly empty space. Now, on top of Rutherford, later on in 1932, James Chadwick came up with the neutrons, and the neutrons were the buffers that prevented positive charge and from repelling each other. All right, let's go back to the 1800s with Antoine Lavoisier, and Antoine Lavoisier came up with the law of conservation of mass, where no mass is lost nor gained, and matter is neither created nor destroyed. He postulated that you could never create an atom or destroy it in a chemical reaction. All you're really doing is rearranging the way the atoms are grouped, and that's how we believe it. We see it today in chemical reactions. So the conservation of atoms is really important to us, especially when we start talking about nuclear reactions, because however many particles or atoms you begin with in the reaction, you must also end with at the end. Up until this point, till Henry Becquerel, everybody thought that atoms could neither be destroyed nor could they be created. But with Henry Becquerel, as he was observing uranium, he noticed that things would just spontaneously emit. And the same thing with Marie Curie and Pierre Curie. They noticed with former elements that this happened, and so they came up with radioactivity, and that is the spontaneous emission of various particles from unstable nuclei. And this is what we're going to focus on, how a nuclei emits and creates a new element. So let's go ahead and talk about this the nucleus, and how it's stable. And let's get a couple of definitions. The first one is nuclear binding energy, and that is the energy released when the nucleus is formed from nucleons. And again, nucleons right here are basically your protons and neutrons, particles within your nucleus. And binding energy is basically, as you increase the energy, the more tightly the nucleus is going to hold together and the more stable the element. So there are two important nuclear forces. The first one is short-range attractive forces that hold the nucleus together. And the second is repulsive forces between protons that are trying to pull the nucleus apart. Remember, protons, if you have two protons together, since they are positively charged, they are not going to attract. They're going to repel each other. And so you really have to know that the reason why we have neutrons is to act as a buffer, so it prevents this whole entire idea of the nucleus falling apart. So the nuclear stability of an atom really depends upon the nucleus, and basically that means the number of protons, and number of neutrons. And this stability really is all about the ratio between the number of neutrons and protons. So this is what we would like to call the band of stability, and the band of stability is a graphical representation that shows you where the cluster of stable atoms lie, and it's typically written the ratio of the ratio between neutrons and protons. So just to recall, N is your number of neutrons, so neutrons, and Z is your number of protons. So it's neutrons to protons. Oops, this is really nasty. Let me rewrite that. Okay. Okay. This is the band of stability. Now, if you notice, I have a N to Z ratio of 1 and N to Z ratio of 1.5. All the stable elements are within those two lines. Those are all stable elements. And so in order for something to be stable, or an element to be stable, it has to fall between the 1.5 line and the N to Z 1 line. How do we determine this? Good question, and here is how we do this. So the ratio of protons to neutrons determines the stability. And if you have the smaller the elements they are, so basically the elements that are in the first to the third period, they have to have a neutron for every proton to be considered as stable. And if you're larger, the larger you get, you have to have at least three neutrons for every 2 protons. So here's the band of stability you saw a couple of slides ago. And if you look in the periodic table, every element between hydrogen and potassium have to have a 1-to-1 ratio, meaning that you have to have 1 neutron to every proton. And every element between calcium and bismuth have to have a 1.5 to 1 ratio, which is the same as 3 neutrons to 2 protons. And everything past polonium are mostly unstable nuclei. So when we're trying to calculate the stability of an atom, we really have to look at the number of protons and the number of neutrons. So let's go ahead and calculate it. So just a quick reminder, if I look at the first question, it says sodium 25, is that a stable atom? 25 is not our atomic number, it is our atomic mass. Okay, you have to look on the periodic table to look at the atomic number for sodium, and the atomic number for sodium is 11, and that also tells us the number of protons. Okay, since we know the number of protons, we can determine the number of neutrons, and the number of neutrons is the atomic mass minus the number of protons, which is 25 minus 11, which is equal to 14. Now we got to do the neutron to proton ratio, and that would be 14 to 1 to 11. But if we simplify this, this is 1.3 to 1. And if we look at the table before, in the slide before, it says there are any elements between hydrogen to potassium, and sodium falls between hydrogen and potassium. It has to have a 1-to-1 ratio. So this is not a 1-to-1 ratio. Therefore, this is an unstable isotope. If we look at the next one, it says osmium 188. Osmium 188 has an atomic number of 76, so the number of protons equals 76, and the number of neutrons would be 188 for the atomic mass minus 76, which is the number of protons, and that gives you 112. Let's go ahead and do the ratio for this, N to Z, and you would end up with 112 to 76, and if we simplify this, it would be 1.5 to 1. Osmium falls between the next level, and remember that goes all the way up to bismuth, and that should have a 1.5 to 1 ratio. And again, we have a 1.5 1 to ratio, so this is a stable isotope. And so finally, let's go ahead and look at francium. francium is past business, so polonium and up. Even though every element after polonium and after are supposed to be unstable, it might not be the case. It might have a magic number that allows it to be stable, but so we have to calculate it. If we look at francium, we can look at the number of protons, and that is 87. And if we look at the number of neutrons, the number of neutrons would be 223 minus 87, and that should equal to 136. If we do the N to Z ratio, you have 136 to 87, and you end up with 1.6 to 1, and this is not within the band of stability, so this is actually unstable. And hopefully now that you know how to figure out the unstable, we can go ahead and move forward. So why does the N to Z ratio change as an atom gets heavier? This really is all about the number of neutrons. The more protons you have, the more repulsive forces you have, and so you have to have enough neutrons to negate that. So the key question is, why are most atoms with atomic number greater than 83 unstable? Well, it's because the 83, you have a lot of protons, and if you don't have the right number of neutrons to negate it, then it's going to just be unstable. And typically, for the most part, they are too many protons than neutrons. Now there's always the island stability, and the island stability has elements that have this magic number where you have enough neutrons that negate these repulsive forces, and so this is where these heavy atoms are stable. So what happens to the unstable atoms? They have to undergo radioactive decay until they become a stable element. And so these so the definition of radioactive isotope is basically that you have atoms that undergo radioactive decay, and typically these are the atoms that are heavy and have too many protons or too many neutrons. And hopefully this is, you can now answer the questions that are in your packet, and I will see you in class with any questions that you have.